So we saw how to compute adjusted heat yield based on the completeness of combustion and fuel moisture and the composition of the fuel. And now we can also estimate the temperature of the gases, the mixture of gases that came out from the combustion. And that's what you have here in this side. The estimate temperature of the mixture of the gases of the combustion. So in order to have that, you have also to have an estimate of the products themselves, and of course they change with the completeness of combustion. So, and you have to understand now what is their heat capacity of the mixture of the products. And here in the spreadsheet you have some reference values for heat capacities for the different components of the system of the mixture between gas and the products of the combustion. So this could be of interest for many reasons, and you'll see that later. But the interesting thing is to know that the estimated temperature of the mixture does not depend very much on the initial temperature of the fuel. So if you start with 298K of fuel, let's change it another 10 degrees, 308, and it changes from 2143 in 53 to 2155. So a 10-degree increase in the initial temperature of the fuel will have a 2-degree increase in the estimated temperature of the mixture. So it doesn't really matter very much what is the initial temperature of the fuel. But a different thing is with the relative humidity of air and air temperature, and they are both very well correlated. So if you change the relative humidity of air from 60% to, let's say, 90%, this value decreases significantly. Of course, now you have 2138K. If you add 60%, you have 2155, because the water really made the air moisture really made a difference. And of course, if you decrease that percentage of relative humidity in the air from 60 to 20%, the estimated temperature of the mixture would increase much stronger. So there is less moisture in the air, and of course the temperature will increase substantially. So this is, and also we can, these two figures are quite well correlated, and we can also change the air temperature and the combination of the two, and they only can be seen as the inputs of air together. So that's the kind of data that we generally have for air, the conditions of air at the time of the fire, the air temperature and the air relative humidity, and with that we can see that there is a certain effect on the estimated temperature of mixture, but it's not a whole lot. The estimated temperature of mixture is much more dependent on fuel moisture, for instance. If you have from 0 to 1 fuel moisture, and you see that is a dramatic decrease of the temperature of the moisture. So you go back again to 0 fuel moisture, and you see it's more than 2000. If you have 100% fuel moisture, you are 1500. And of course the same thing with the equivalent air to fuel ratio. If you go from 1 to 0.8, you also decrease substantially the temperature of the mixture of the gases that are produced by the reaction. So now we have, let's say, all the possibilities, and we know how these inputs can be used to generate these outputs. And using the spreadsheet, you can look at it to look some intermediate steps. So the equation of combustion in air with all the figures and all the calculations. You can look at the intermediate steps that were used to calculate the heat of combustion and heat yield, and you can also look at what were, let's say, the emission factors that were calculated in order to estimate the emissions from that fire. So I hope with this you have a general picture of the possibilities for using this spreadsheet and try to use it and relate it with the conditions of your fire.